Okay, welcome everyone. I think we'll get started for tonight. So hi, my name is Hannah Fronenberg. I'm a PhD student here at the TSI, the Trottier Space Institute, and your moderator this evening. And I guess welcome to the very last public talk for the 2022-2023 academic year. So before we get into the talk for this evening, I just want to go over a few quick announcements. So the first one is just a big thank you to everyone. So this is the last talk of the academic year, and we've had 9 amazing public lectures this year. And you know, we wouldn't be doing this if we didn't have an audience like you that shows up every single month without fail and is, you know, curious about all of these different topics. So thank you so much for supporting us here at the TSI and for your curiosity and for your questions. You know, we really learn as much from you as you do from us, and it may not seem like that, but really we do. So thank you. The next thing is this is our code of conduct, so I'll just leave that up for a moment for everyone to read. But if anyone has any questions or needs any help while you're here, feel free to contact either me or Carolina, our other organizer, who will be here in a moment, or we have some volunteers throughout who are sitting here at the front, so you can come find anyone. So that brings us to our talk this evening. So tonight we'll be learning about how a cosmology experiment, which aims to observe the most distant light in our universe, and how that was used to unexpectedly study our very own solar system. So Dr. Jack Orlowski-Scherer is a cosmologist and TSI postdoctoral fellow who works on the Atacama Cosmology Telescope in Chile. And his research took an unexpected turn when a group of physicists in the collaboration realized that they could observe hundreds of asteroids in our very own solar system with the same instrument that you use to measure the cosmic microwave background. And so today, Jack will tell us about all of this exciting new stuff in his research. Afterwards, we'll of course have the Q&A period as usual, where you'll be able to ask all of your most pressing questions to our expert speaker. So with that, I will pass over the HDMI cable to Jack, and we will just need one moment to reshare the screen for everyone online. So everyone online, bear with us one moment.
I have to make sure when I pop this in the slideshow that it doesn't disappear for people on Zoom. I don't know if anyone's there who can say whether they can see. Well, anyway, people can't see it, they can complain on Zoom. Thank you for that introduction, Hannah. I'm Jack. I'm a postdoc here at McGill. I work with Drs. John Severs and Cynthia Chang. I'm primarily a cosmologist, which means that I'm concerned with very large structures in the universe. I don't typically think about anything much smaller than galaxies. But through a series of happy coincidences, I was led to start thinking a lot about asteroids and specifically what they're made of. We do know that they are made out of things, but what they're made of is an open question. So that's what I'm going to talk about today. So I'm going to start with a little.
Share your screen. Very glitchy.
It's very glitchy on the Zoom.
People online, like
yes, it's like flickering.
Yeah.
Let me try sharing it again. Is that any better?
Perfect.
Okay, great. All right, so I'm going to start with a little info on our solar system. So our sun, like many others, was initially a ball of gas, and that ball of gas collapsed under its own. I'm sorry, I forgot to set my timer. There it goes. Collapsed under its own weight, and it collapses down, and it radiates heat out, and eventually it collapses enough that the star or the protostar at the center of that ball of gas can begin undergoing fusion, and that forms a star. And then the remainder gas and dust in the system typically forms a protoplanetary disk. So that gas will initially have some angular momentum, and much like if you're making a pizza pie, right? You throw it up in the air and it spins and it flattens initially a round ball of dough. As you spin it in the air, it slowly flattens into a pizza pie. As that gas and dust collapses in because of that initial angular momentum, it flattens out and forms a disk. And a disk that keeps its initial angular momentum. As it flattens, you start to form protoplanets. What's a protoplanet? It's just a little bit of matter in this protoplanetary disk. So you start with individual grains of dust, and those sort of collide together and form bigger grains of dust, and those collide to form very little rocks, and the little rocks collide and make bigger rocks, and then eventually you have things that we would consider to be macroscopic, macroscopic size. They collide together. Eventually you build up things big enough that we call them planets. And what the planets do is that they clear out. What makes a planet special as compared to like an asteroid or something like that is that a planet clears out its orbitary path. So within the path of a planet, 99.9 or whatever % of all the material is on the planet. There are no other objects sharing the orbital track with the planet. Once those planets form, however, there's still lots of material left over in the protoplanetary system, and it has to go somewhere. It either collides with the planet and ends up there, or it enters a stable orbit outside of the sphere of influence of the planet, and we call those objects asteroids. Typically, there's actually a lot of other areas where these objects exist in our solar system. So the asteroid belt's probably the most famous, but there are other reservoirs of asteroids. For example, the Centaurs, which are a group that follow Jupiter around. There's the Kuiper belt and potentially the Oort cloud, which is a reservoir for comets. And we care about this because, sorry, let me just quickly explain this graph or this diagram on the right, because it's one of my favorite. That's a picture of a protoplanetary disk forming around a young star, not pretty far away from us. That ball at the center is not actually the star. You can't see the star here. That's hot gas surrounding the star. But what you can see is that sort of band-like structure. And each one of those dark bands is actually a planet. The band itself isn't the planet. What the dark band is a gap that's been cleaned up by a planet that's forming in this disk. So we can actually, this is an amazing photo. We can actually see planets developing in real time. But you can sort of see what I'm saying, that the planets start to clear out their orbits, and then the other material, which in this case is still relatively unconsolidated, ends up sort of spread out throughout the rest of the solar system. I can't make it go forward. And so that makes asteroids leftover of our solar system formation. That diagram on the right is just showing you what I talked about earlier, where you start with a ball of gas and collapse it down into a solar system. And so as sort of relics of planetary formation, they tell us a lot about what materials were present and in what quantities in the early solar system, and therefore a lot about what our early solar system was like. And so if you have a theory of solar system formation, it's going to predict a lot of things about asteroids. It's going to predict how many of them we see, it's going to predict their sizes, and it's going to predict their compositions. And so if you have this theory about how asteroids form, you want to go look at asteroids in order to, if you have a theory about solar system formation, so more general, you can verify that theory by looking at asteroids and seeing if it matches up with what your theory says. Of those things I talked about, the size distribution of asteroids is relatively well understood. And for reasons I'll get to in a second, what the surface composition, meaning the materials that are on the surface of the asteroid and the materials that are in the very core of the asteroid, are relatively well understood. What's not well understood is the region that's immediately below the surface that we call the regolith. That's a fancy SAT word that you can take home for today. So this diagram on the right is showing like a cutaway of an asteroid. So you can see that the regolith is right up there at the surface, but it's pretty deep on a typical asteroid. It's a few centimeters deep. And then there's other stuff below it. I'm not going to get into today. Frankly, I don't know that much about it. And where we come in is that regolith has previously been pretty inaccessible to astronomers. We couldn't see into it, and we don't have, well, we do have asteroids, but I'm going to put an asterisk on that, here on Earth, so we can't really study it. It's difficult to study. But it turns out that the regolith, that the surface of asteroids is actually transparent in the microwave. Just sort of luck of the draw, the surface materials work out so that if you look at an asteroid in the microwave or millimeter wavelength, you actually that surface is a little bit transparent, kind of like cloudy plexiglass. You know, you can see a little bit into it, but not all the way. And so if we look at asteroids in the millimeter, it tells us about what's going on in the regolith and gives us a new picture into asteroids that we didn't have previously. So how have we observed asteroids in the past? Well, there's a couple ways you can do it. First is that you can look at asteroids that crash into Earth. You know, we find remnants of asteroids all over. The pros of that is obviously you can get up close and personal. You can dissect the asteroid. You can kind of do, whatever you want with it, which is great. The downside is that only the core survives, right? Coming into Earth's atmosphere, very violent event. Most of the asteroid burns out on the way down. And also you get a very biased sample of asteroids, small asteroids, and then tend not to make it to the surface. They burn up completely before they make it down here. And also the composition of the asteroid depends changes how likely it is to actually impact and leave a remnant. Metallic asteroids are much more likely to leave behind a nucleus or whatever it's called. The next thing you can think about doing is sending a spacecraft to visit an asteroid. That's sort of what I'm showing on the right. That's actually a comet. I'm cheating a little bit, but it's close enough for our purposes, and it's a really cool video. So this is a photo actually taken from a comet by a satellite, and you can see the surface of the asteroid. You can see how that stuff whizzing around. So the stuff sort of moving uniformly down. That's actually just that's the stars in the background. The stuff that's sort of floating all around is actually little bits of the regolith that are flying around the surface of the comet. And so this is great. You can get really up close and personal with an asteroid. You can dig into its surface. You can learn a lot about it. The cons are, of course, that space launches are extremely expensive. And so, you can only do so many of these, right? We have a very small sample. We've sent asteroids to I want to say about half a dozen comets and asteroids combined. So it's a very, very limited sample that we can afford to do. The third thing you can think about doing is looking at them with telescopes. And telescopes are great because they're relatively cheap. You can spend as much time looking at asteroids as you like. And they allow you to see, as many asteroids as you want, right? You can just keep looking. However, you have to do a lot more work to figure out what you're seeing. Unlike with landing on an asteroid, we don't get the full picture. Like when we look at an asteroid with a telescope, we don't see that, right? Like I wish we did, but in most cases, what you see is just a point of light. The asteroids are just point sources of light to our telescopes. In some cases, you can actually resolve the asteroid, which I'll get to, but in most cases, you can't. And one other point I want to get into before I get to in this sort of preamble, because it'll be important later, is that asteroids exist in color, which is obvious. But the important thing is that the color of the asteroid tells us about the material properties, right? Much like how we can just sort of heuristically look at something, get some sense of its material property from what it looks like. So too with asteroids. And so it turns out that the spectrum that you see, meaning the amount of light as a function of wavelength, is very sensitive to the material that the asteroid is made out of. So this is that picture is from a lander. That's a false color image of an asteroid. The coloration has been exaggerated, but what you can see here is that there are red and blue portions of this asteroid surface, and that's real. What you're seeing is rocks that are redder than other rocks. It's been exaggerated here. They probably all look brown in real life, but the point is that we can see the color variation in the surface of the asteroid. You can, so traditionally that's been done in the optical IR. This is telescopes like WISE, the Wide Field Infrared Survey Experiment, or James Webb, although this is not the primary science goal of James Webb. And that's great, but the limitation here is that optical and IR are very short wavelength, and so they're only sensitive to what's going on at the absolute surface of the asteroid, meaning the first few tens of microns, so 10 to the minus 6 meters, a very, very small distance into the asteroid. You can also do radio observations. So the asteroids don't actually emit in the radio, but you can do something kind of like radar, where you send out a radio wave, bounce it off the telescope, and observe the reflection from the asteroid. And that tells you a lot about the shape and spin properties of the asteroids. And then finally, like I said, microwave, that's the subject of this talk. These are telescopes like ALMA-RACT, which I'll talk about in a little bit. And as I said, because the regolith of the asteroid is slightly transparent, these allow you to see a little ways into the inside of the asteroid. So IR observations, like I said, they tell us about the surface. They tell us a couple things. They tell us about its temperature. So we can infer the temperature from the spectrum we see. They tell us about how reflective it is, which is essentially just how shiny the asteroid is. And they can also tell us something about the properties of the asteroid from this, from additional features of the spectra that we observe. So when we look at in the IR and optical, we're seeing a combination of two sources of light. About half the light we see is reflected. So this is, light comes from the sun and hits the asteroid, and some of it's absorbed and some of it's reflected and comes back to our telescope. And so we see that. And then about another half of it is the asteroid's thermal or black body emission. So all objects glow due to self-emission. Objects that are hotter glow more brightly. And so we tend to only think of very hot objects as glowing, but every object is glowing very slightly. And the asteroids emit about half of their light that way. And so that gives you information about how warm the asteroid is. And so that also tells you that the sort of the balance of those two tells you about the material properties of the asteroid. So radio, so like I said, radio, asteroids don't significantly emit in the radio, but you can bounce radio waves off of them and take images of very high resolution. So this is the now sadly defunct Arecibo telescope in Puerto Rico, I believe, right? Anyway, which is a huge, like 300-meter dish. And there are other similar dishes, but this was for a long time the premier telescope for looking at asteroids in the radio. So this is a little schematic of how that works. You can see the radio dish emitting a signal, and it hits the asteroid, and that reflection is slightly delayed depending on the exact shape of the asteroid. And so you send out, oh, you can't see the font at the bottom now. You send out this pulse, which is initially just very sharp peak, and it gets smeared out something by the shape, some by the shape of the asteroid. And if you're very clever, which I'm not, but the radio people are, you can reconstruct the shape of the asteroid from how exactly that peak gets smeared out. And so if it'll go forward, this is what that actually looks like. So Arecibo here is actually up at the top of the screen, beaming down. And so you can see, I don't actually remember what asteroid this is, but this is an asteroid that Arecibo took a photo of. And you can see, you can just see by eye the shape of the asteroid, which is very cool. You can also see their rotation. So if you just keep looking as the asteroid moves, you'll be able to see it rotate. And that's what you're seeing here is the rotation of an asteroid. And the sort of variation you're seeing is changes in the surface reflectivity of the asteroid. Also really cool, you can maybe just make out that little dot moving sort of down from the top. That's actually a moon of the asteroids. That's a tiny little fragment of rock that's orbiting this asteroid that they happened to see when they pointed the telescope here. So cool photo. So now on to the meat of the talk, the microwave observations. So we've painted this picture. We have this long-standing history of observing asteroids in the IR and in the radio, and in particular in the IR, we get an idea of how hot those asteroids are and how reflective they are, and so we can make a prediction based on that of how much light we should see when we look at the asteroid in other wavelengths. And so people have done this before in the millimeter, and we've consistently found that asteroids are less bright in the millimeter or microwave than expected, meaning there's less flux coming in. And so the thought here is that probably things are changing beneath the surface, right? Like I said, the IR is only sensitive to just that skin of the asteroid, but the millimeter observations can actually observe up to a centimeter or so deep into the asteroid. So quite a ways down. That's several orders of magnitude further than the IR. And so the thought is presumably something is changing inside this asteroid so that things below the surface aren't the same as what we'd expect from right at the surface. And that's really cool. That's a good thing to know. That gives us information about asteroids that we didn't have before. So the sort of premier instrument for doing this is called ALMA, the Atacama Large Millimeter Array. That's a photo of it on the right, which is a super high resolution millimeter experiment. It actually did that picture of the protoplanetary disk all the way back from slide 1. So it's a really high resolution, really sensitive experiment. The problem is that their observations take a long time. ALMA can really only look at one thing at a time. And so it's in very high demand and very short supply. And that means that its time is expensive, not literally in terms of money, but in the sense that, you know, it's very hard to get observing time. You need a really, really good reason to look at something with ALMA for them to let you look at it. So occasionally that's the case, but almost not going to take, you know, it's not going to take a month out of its observing time to go do a catalog of asteroids. It just has much, much higher priorities. So what's the sort of solution to this? So the solution to this is millimeter survey observatories, and specifically their cosmic microwave background experiments. So you may have heard of the cosmic microwave background at previous talks here. I'm not going to go crazy into it, but it's leftover relic light from the Big Bang. And there are all these. There's a couple of experiments that are dedicated to observing the CMB in wide fields, meaning that they observe a large portion of the sky and they just sort of, you know, survey it back and forth all day, every day. And so just sort of by coincidence, these actually do a pretty good job of looking for asteroids in the millimeter because they're observing at the right wavelength. You also have many, many years of observing that you can add up. So they end up with good sensitivity, not quite as good as ALMA, but actually reasonably comparable. This is a South Pole telescope. This is not an experiment. It's a CMB experiment at South Pole, as the name would suggest. And they did this about 2 years or a year and a bit ago. And they went through and they looked for asteroids in all of their archival data, and they managed to find 3. And that's not because they're not a great experiment or they don't know what they're doing. It's because they're at the South Pole, and the South Pole faces down, and the plane, and then the asteroid belt, right, is our orbit, our spin is slightly tilted with respect to our orbit, but it's mostly aligned, right? We're sort of spinning like this. So if you're at the South Pole, you can't actually really see the asteroid belt. So that picture there, that faint dotted line, not the bright green line, that's actually the galaxy, but that faint dotted line that's doing sort of a sine wave thing, that's the plane of our solar system, which is the plane of the asteroid belt. And then all those boxes down there, you don't need to worry about the details, but those are different areas of the sky that the telescope can see. And you will note that they kind of get close to the line around there a little bit, but they don't really overlap with the asteroid belt. And so, of course, they don't see very many asteroids. So that's sort of it for them, but they can't really move their telescope. Or it's extremely expensive to move their telescope. So they're sort of limited. That's where my experiment steps in. So I'm a member of the Atacama Cosmology Telescope. And if you know where the Atacama is, you'll know that it's in Chile. It's in North Chile, a little south of the equator, but relatively centrally located on the Earth. And so it is very well able to see the asteroid belt. We can see about 40% of the night sky in something. I haven't done it exactly, but I think it's like 85 or 90% of the asteroid belt. So nearest makes no difference, the whole thing. Much like SPT, it's been running for about 15 years, so we get great sensitivity. And we also, and SPT also does this, observe at 3 frequencies. So that gives us the ability to sort of probe various depths into the regolith. So each one of those frequencies, right, is going to pick out a slightly different distance because it'll be absorbed by the asteroid at slightly different rates. The problem, of course, is that recovering these asteroids is challenging. So ACT does not take pictures like most telescopes you're used to, right? You're probably used to like James Webb or Hubble pointing the telescope over someone going and taking a picture. That's not what we do. It's much closer to taking a video. We just sort of scan back and forth on the sky, and we constantly have our detectors running. And then we figure out where the telescope was pointing at a given point in time, and from that way reconstruct what the sky looks like. This is really good if you're looking at things that aren't changing, like the CMB, right? Imagine taking like a very long exposure photograph, right? Things that aren't moving are going to be crystal clear, and anything that's moving is going to be blurred out. That's our problem. The asteroids get blurred out. So what we have to do is essentially figure out what individual frame the asteroids are in, and then go take a little cutout where the asteroids are, and then use those images for our analysis. So just a little bit about, like I said, we can think of these as like long exposure photos. So we just sit there. Here's how we observe. We just sort of go back and forth like that line does, and as the night progresses, you know, the night sky rises through our field of view, and so we get this sort of natural drift of our telescope through the sky due to the motion of the Earth. So this is from our perspective. If we instead go to the celestial perspective, it looks like this. So now the Earth is moving and the galaxy is still, and you can see that we make this sort of serpentine winding path through the night as the sky rises. And it's just one more picture showing that it's basically saying the same thing, but that top red line is sort of the fixed scanning, and you can see as you go through the night, eventually you wrap back around where you start. So the thing that we do is actually we let the camera sort of run forward until we get back to where we started, and then we cut it off. And now we have essentially a picture, right? We've got a picture of the night because we haven't gone over any points twice. At each point, there was only one snapshot that went into that point in time. So we can take those maps and we can look for asteroids that way. So this is what you see. This is actually, I'm going to start with some SPT images. So these are the 3 asteroids that SPT saw. They don't look like much. They look at like dots of light. Like I said, they're just point sources. But the important thing is that you can measure the amount of light that you see from these asteroids. And that's what you see here. And so you can see that they show up on the right, but not the left. And that's largely due to the variation in brightness due to the thermal spectrum. So like I said, these asteroids emit due to their temperature, much like something that's red hot will glow. These asteroids are glowing. They're just glowing in the millimeters, so you can't see them because your eyes aren't sensitive to the millimeter. But it all has this sort of characteristic shape. You don't need to worry exactly about the Planck's law. I'm not going to quiz you on it, but the point is just we understand well what Planck's law is, and we understand if you have a black body, how the fluxes should be distributed. And so by looking at something like this, you can essentially say, does the flux that I see, or the brightness that I see at one frequency, does that match what I see at another frequency, under the assumption that it's a thermal emitter? And the ACT results, the SPT did not have enough asteroids to say anything about this, right? 3 is not particularly statistically significant, but ACT sees about 180 asteroids, mostly due to our much larger field of view. And our data indicate that something is changing under the surface. Whether that's temperature, that could be the temperature of the material, it could be the density. We're actually not totally sure yet. Can I go to the next slide? Yes. So, one sec. One way we can sort of break this up to get a better picture of what's going on is to break things down by asteroid class. If you take a picture of an asteroid in the IR, you can break the asteroids up into different groups based on their spectra. So their wavelength is their brightness is a function of wavelength. Those look different, and that grouping actually maps very well onto the material that the asteroids are composed out of. So asteroids that are made out of similar material tend to have similar spectra. That's what I'm showing here. That one on the right, so there's a lot of types, but the two biggest ones by far are C-type or carbonaceous asteroids, and S-type, which technically stands for silicaceous, but it's much easier to remember it as stony asteroids. So carbonaceous is a fancy word for meaning carbon-like. So these are asteroids that have a lot of carbon. Stony asteroids are what they sound like, they're stone. And that material property has an effect on what they actually look like. So this is an image where the fancy word is albedos of the asteroids have been normalized. And so this 253 Methilde over here, I think that's how you pronounce it. That's a C-type asteroid. And you might even struggle to see it against in the projector screen because it is very black. It is almost completely black. On the other hand, Eros and Gaspara over here are S-type asteroids. They're rocky. They're much brighter than the black asteroid. And it goes beyond just how bright and shiny they are. The relative fluxes at different wavelengths are also different for these asteroids. And so you can ask, well, if we take our millimeter observations and we break them up by asteroid class, do we see something different? The answer is yes. So this is preliminary, but we're pretty confident in this. So you can ignore the M, X, and P asteroids over here. They're minor classes of asteroids. Just sort of focus on the C and S type asteroids over here. So you can see that the red is showing you the full distribution of all the emissivities. So this is, on the y-axis is the brightness of the asteroids, and on the x-axis is just the different classes. The colored bands are giving you the full population distribution. So that's essentially showing you where it's skinny, there are not many asteroids that are that bright, and where it's fat, there's a lot of asteroids that are that bright. And those black dots with the little error bars are showing you the average within a population. So it's just averaging over those distributions. And what I want you to take away from this plot is you can see that black dot for C is pretty much on that 0 line. That's a very special line. That's the expected value from IR observation. So if you lie on that line, you are a black body that agrees with what we see in the IR. If you lie below it, something's going on. And you can see that those S types align pretty significantly below the line. And the really interesting thing, so this is at 90 gigahertz, which it's just one of our observing frequencies, which I think it's about a millimeter. I can't do the conversions in my head. But what's really interesting is that it changes based on the frequency. So this is 220, and you can see, firstly, about 220 gigahertz. You can see, firstly, that they've both moved down, right? So now the C-type dot is also significantly below the S the line, and you can also convince yourself the S-type has moved down as well. The other thing that's interesting is that they've gotten closer together. That's a little harder to just see on this plot, but you can believe me, there are actual numbers associated with that data. So you look at the actual number, and they're a lot closer together at 220. So that's suggesting that there's some sort of material, there's something about the material of the asteroids is causing this deficit, right? The fact that C-type asteroids are green, but S-type is suggesting that it's something about the actual materials, and that dependency is pretty complex. It's not just like, S-type asteroids are not as shiny as we thought they would be. There's something more challenging going on because the amount of deficit that you see is a function of the wavelength and the class. And what's extra confusing is that 220 gigahertz is actually closer to the IR observations than 90. 220 gigahertz. So IR is like a few terahertz typically. So 220 gigahertz is closer to a terahertz than 90. So here, like my intuition would be that stuff, closer to IR would match the IR better. And yet that's the opposite of what we see. And that we actually, this is some really good science because we don't actually really have an explanation for why that's happening. So yeah, like I said, we're not 100% sure exactly what that mechanism is that's causing this yet. Basically, the only plausible explanation we've come up with is that the asteroids are way colder inside of them, and so go back to this plot. We make an assumption that the asteroids live here in this straight part, but if they were really cold, they might actually sort of live in this turn off part. Which could kind of maybe explain what we see, but not really. So, yeah, it's certainly interesting. So yeah, that's the status we see. So essentially the takeaway is previous people have seen this deficit in the millimeter. We see it too. And whereas previously we could only look at 1 or 2 asteroids in the millimeter, with our experiment, we've been able to look at hundreds, and so we can say something statistically about whole populations of asteroids. And what we can say is that, yeah, it's pretty clearly tied to their composition because the amount of deficit you see is a function of their class or their asteroid composition. What way exactly, I'm not sure yet, but this is something we didn't know before. One other thing you can do, so you can look at the sort of instantaneous fluxes, but you can also look at how much asteroid flux varies. This is a really cool video one of my collaborators put together. That's the asteroid, or really more like a minor planet, Ceres. And that's our real data, by the way. That's each one of those frames is a raw image from our telescope. And you can see it blinking like that. And it's not because it's like turning on and off or anything like that. What's going on here is that Ceres is moving closer to and further away from us, right? Because we're orbiting the sun and it's orbiting the sun. The distance between us gets closer and further away. And so much like, any source of light, the further you move it away from you, the dimmer it gets apparently. The apparent brightness of Ceres is changing with distance. And we know how to account for that. And so we do. And so you can remove this blinking, and what you're left with is the variation in the light curve due to the asteroid's actual rotation. So this the idea here is, your asteroid is rotating, so it's going around the Earth, but it's also spinning on some axis, much like the Earth is spinning. But unlike the Earth, asteroids are pretty non-uniform. So Earth is very big, and so the centripetal force more or less requires it to be spherical or very close to spherical. It's a slightly compressed sphere, but anyway, very close to uniform. Asteroids being much smaller can be much more irregular. I mean, you saw that video before of the asteroid that has like this huge, or the comet that has this huge cliff wall in it, right? And so as it rotates, 2 things can happen. One, the cross-sectional area of the asteroid, from our perspective, changes, right? Imagine if you have a football, you hold it like in one way and it's big, and you hold it the other way and it's small. And so that changes the amount of light that we see from the asteroid. You can also have variations due to actual variations like in the surface properties of the asteroids. You can imagine having like a dark spot on the asteroid or something like that. And when that swings around to point at us, that changes the amount of light we see. And so people have done this a lot in the optical and IR. And so the question is, can you do that in the millimeter? And does what we see in the millimeter match what they see. And the answer is yes, we can do it, but unfortunately, we don't quite have enough sensitivity yet to say if what we see matches the IR. So it's excuse me. This is exactly what I just described. This is an asteroid. This is the flux. Phase here is sort of just, you can think of this as running from around one orbit of one rotation of the asteroid. So that's 0 rotations, that's halfway around. And over here is all the way around. And then this is just the flux normalized to some quantity. It doesn't really matter. The point is just that it's changing. And so those blue data points are the fluxes, and you can see this pretty nice clean sine wave in it. So people have done this in the millimeter before, but it's certainly the first time anyone's ever done it with a survey experiment like this. So we see 2 asteroids with significant with phase curves that look nice and neat like this, and then we see a whole bunch that look kind of like garbage that are clearly varying, but are varying in very unusual ways. That's not necessarily unexpected. If you have really ugly things going on in the asteroid, it can generate some really gnarly phase curves. But we're still in the process, except for these 2 ones that were nice and clean, and we could just put our stamp on it, put it in the paper, and get it out the door. We're still spending a little time trying to understand exactly what's going on in those phase curves. But the answer is yes, we can do it. And so looking at the future, so the future is really bright for this field. So there's 2 experiments coming online, and at the last couple minutes of my talk, sorry, Mom, can't talk right now. Last couple minutes of my talk, I'm going to talk a little bit about Simon's Observatory. So there's 2 experiments coming online that are going to really increase our abilities in this field. One's called Simon's Observatory. This is essentially a successor to ACT. So that's Simon's Observatory on the right. It's going to do what ACT did, but like 5 times better or something like that. So more of the same, except all those error bars that I showed you get 5 times smaller. So that's exciting. And the other one is called CCAP Prime, a really similar telescope to ACT. It's just going to be operating at slightly shorter wavelengths. That's a typo, slightly higher frequencies. And so that's really exciting because it's going to help us understand this sort of unusual behavior in frequency. The more frequency channels we have here, the better our ability to sort of pin down exactly what's happening. So I have a few more minutes, and I put these in as my backup slides. But so I do a lot of analysis work, but I also do a lot of instrumentation. And in particular, I'm also a member of Simon's Observatory. And so I did a lot of design work for Simon's Observatory and was lucky enough this January to get to go down to the site in the Atacama where both ACT, the Atacama Cosmology Telescope, and SO are going to live. So I figured people always like pictures of the site. So that's SO, that's the LATR. That thing currently looks like that. So that's the concrete foundation for the telescope. This is, by the way, the Atacama, the reason why we go there, very high, very dry, the two things that you're looking for sub-millimeter observation. So it's a desert at about 17,000 feet of altitude. So very unique location. It also sucks. If you have never been that high, 17,000 feet of altitude is brutal. And it's a desert, so it's unbelievably dry. So you're constantly struggling for breath, and everything is like your hands are chapped, your lips are chapped, everything's chapped. Didn't yeah, the environment was not very nice. It was cool. That's a picture of our workspace. You can see we've got the fancy branded Simon's Observatory high vis. That's the actual camera for Simon's Observatory. That's me with it at the site. So we shipped it down in a shipping container. There we are unpacking it. That's a picture of our site team with the camera at the site. So you can see how big it is compared to people. I mean, to get 5-fold better than ACT, you need a lot of power. Don't worry about that. That's what it looks like on the inside. It's really complicated. There's a lot of wires. So I lied. That's what the telescope looked like when I was there. I said that's what it looks like now. That's not actually true. They've made some progress since then. So that's the base of the telescope, and you can see them starting to assemble it. The more extensive structure. There we are at there's me, some of my friends were at the top of the mountain in the background. It's nearly 19,000 feet. Another photo of me and a friend, another photo. We're very proud to climb the mountain. Skip this slide, this picture from the top of the mountain. So this is the site as a whole. There's a whole bunch of experiments up here. Everyone who's doing submillimeter wants to be at this site, so because it's so good. You can see in the, I don't think you can actually see ACT. ACT is here, but unfortunately you can't see it. That's an experiment called Polar Bear. This is an experiment called Class. You can see the weather going by. Oh, and then those are like not, sorry, those are not related slides. Do I have a picture of ACT here? I don't, that's a bummer. So yeah, that's the status of things in the submillimeter. And yeah, I'll go ahead and open the floor to questions. I think in the back first.
Snow is everywhere or only inside the galaxy? Do they travel from galaxy to another galaxy?
No, in fact, they probably don't travel from one solar system to another. So we think that they are born in a solar system and they stay there forever. There's an outside chance that we saw, you may have seen it got a lot of popular science traction, stuff about Oumuamua, which was an object that may have come, that we observed that may have come from outside the solar system. It's really not quite certain, but it is possible that it's from interstellar space. So a very small fraction of these items might move from one solar system to another, but certainly not galaxy to galaxy. And most of them, you know, they're old heads, they're born somewhere and then they die there. I think the other question is,
you were saying that the asteroids are made of this structure. On top there's regolith.
yes.
And let's suppose the asteroid breaks, so we would just have like a knot. Or is there a new layer that forms?
Yeah, so temporarily there would be, yes. So this is a great question. So asteroids are colliding all the time, and so they do split. And so temporarily you would get sort of like a cross section of an asteroid, just like this. But the reason that it's structured like this has to do with the fact that the asteroids are really small, so they don't have a lot of gravity. And so our Earth is nice and compact because it's so big that everything gets pulled down reasonably hard, right? An asteroid being so little, the gravity, the hold that it has on the material is really pretty weak. And so almost immediately it starts to fly apart. And so the regolith is actually not solid like ground here is. It's actually a lot more like snow, like fresh snow. You know how it's very loosely packed and you step into it and it goes down forever. The surface is also like that. The regolith is much more like that. And so if you were to cut it pretty quickly, it just sort of floats away and reforms the regolith on the exposed side. Sort of interesting story about the regolith. So the moon also has a regolith. So much like asteroids, it has a unconsolidated surface. This is why you get such pretty footprints in like the moon from the pictures of the moon landing. However, it was not known exactly how deep the regolith was when the Saturn missions were launched. We had a pretty good idea that it was probably only a couple inches, but no one was really sure. So part of the reason why the lander has such long legs is in case there was a couple feet of regolith, the booster would still be above, would clear the regolith, and it would be able to launch. And there was an outside possibility that they would land and just sort of going into like 10 feet of regolith. So this was considered highly unlikely, and it was in fact unlikely, but they did have, well, they didn't have a contingency plan for that one, actually. That was just sort of a mission critical failure. But yeah, there was an outside, they were prepared for an outside possibility that they just sort of sunk into the regolith, and that was that. So luckily they did not.
It's like
Do you mind? I'm going to go here, then I'll come back to you.
our solar system alternates between in dense matter density, alternates between gas, the sun,
Yeah.
and then rock, and then more gas, and then rock. And do we know why it is so? And if not, with
Yeah.
studying the asteroids help?
No, this is actually a great question, and the answer is that our understanding of this is evolving. So prior to, and I'm not an exoplanet expert, so I'm about to talk about exoplanets. I'm not an expert, so I will probably say little things wrong. But prior to detecting other exoplanets, we thought that our solar system was pretty typical. That you had gas at the center. The sort of traditional thinking was when the sun, you have gas that forms and goes to the center and eventually forms a sun. And the sun ejects a lot of energy back. And the thought was that this blew all the gas out of the inner solar system. And so you ended up with only rocky planets on the inner solar system. And then the gaseous planets could form further out where they weren't so close to the sun. When we started detecting, so that was the thinking. When we started detecting exoplanets, we immediately detected many large gas-like planets that live close to the sun. And so that really challenged that thinking. Now, we're probably biased in what planets we see, meaning that those close gas giants are probably not representative either of what most solar systems look like, but it is probably more complicated than what we thought. So I guess to answer your question, that's an area of active research. And yes, where you see the asteroids has a lot to do with the formational history of the. So one thing I didn't go into here was that where the asteroids actually live is sort of determined, we think, primarily by where the gas giants are in your solar system. And so, yeah, if you in our particular solar system, we only have one asteroid belt to look at. So in this particular case, it only tells us about what went on in our solar system, not other ones. But yeah, it's an open question. Sorry, it was a little roundabout way to say it's an open question, but yes.
Are comets inconsistent in the microwave spectrum?
You know, that's a great question. So we tried to look at comets. And so the problem is that comets are a lot less bright than asteroids. We think of them as brighter, but that's because when you see a comet, it's passing by the sun and extraordinarily bright. Most of its time, it's not doing that bright thing. It's out in the far solar system, and it's actually a lot darker than an asteroid then. So we actually ran our code on a bunch of comets too, because we wrote our codes. We were smart writing our code, and you can just sort of plug in whatever you want. So we put in comets. Unfortunately, we didn't see any. To my knowledge, at this point, no one has actually been able to see a comet in the millimeter. So to answer your question, yeah, we'd really like to find out, but we don't actually know yet. And I think we're probably close. You can do like back of the envelope estimates of how bright they should be, and it's like close to how sensitive we are. So maybe next generation, maybe in like ask me in like 5 to 10 years, I might be able to come back and tell you. But unfortunately, as of now, we can't say. But I think that would be something we'd love to be able to tell. Yes.
We have a question online.
Go ahead.
So all of the asteroids you talked about were from the asteroid belt.
There may be one centaur, but yes.
Okay.
The vast majority of them are from the
Because
asteroid belt.
this person is asking, are you able to observe near Earth asteroids with a microwave telescope? Basically, and maybe they're getting at, like, can you save us from the asteroids?
So one thing I didn't go over here, I said we had hundreds of asteroids. That is very impressive. WISE has seen hundreds of thousands of asteroids. So we're actually not good. We didn't see any new asteroids. All of these asteroids were known in the past. And the issue is really that just the asteroids are a lot brighter in the infrared than they are in the millimeter. We do have an advantage, which is that the further out you go, the more relatively bright asteroids are in the millimeter. So if you go very far out, meaning beyond the orbit of Pluto, we do actually win out again. And that amazingly is actually the progenitor of this project. Was we were looking for objects outside the orbit of Pluto, and we did all this work, and then we didn't see anything outside Pluto, and then we were like, wait, can we see things we already know about? So we went and checked the asteroids, and lo and behold, they showed up. So yeah, sort of a winding road to get here, but closer, certainly not. Anything that's very close to Earth, you would see in the optical or IR long before we saw it. Yeah. Yes.
So what do these results have to say about our solar system models?
That is several steps from where we are right now, unfortunately. Yeah. But it does, but so that's the sort of grand motivation. The more sort of small scale motivations we'd like to figure out if the sub-millimeter or millimeter emission gap is due to surface properties. It is due to the material, excuse me, due to the material properties of the asteroid. At this point, we can pretty conclusively say that yes, it is down to the fact that there's something about the material of the asteroids that's changing under its surface. So the next step would be to understand what exactly it is that's changing under the surface. Could it be the it could be the temperature, it could be the emissivity or something like that. And we're still working on understanding that. And then that would say something about theories of solar system formation, because it would tell you what exactly is in the asteroid. And so that sort of tweaks how much metal, how much like the relative proportions of like metal and stone and stuff like that in the early solar system. And so that would be an actual check on like a solar system formational theory. Yes.
And are there like bounds we can set on the materials like in these asteroids just due to gravitational properties? Ferocity.
Sorry, what do you mean by that? Like,
Well, like, aren't there like certain materials for which the asteroid like won't stay together?
oh, yes. So the issue is this maybe oversells these sorts of photos of the radio, maybe oversell in general how good we understand what asteroids look like and how big they are. For most asteroids, we have generously no clue how large they are. That's a bit harsh, but our understanding of the actual size of the asteroid for anything smaller than like 100 kilometers has pretty big error bars on it. And so that goes as like, volumes like the scale to like third. So there are huge error bars on the volumes of this thing, which means there are huge error bars on the density. Which means, unfortunately, that's not a great way. You do get some limits from that, like especially for the larger asteroids, like we can put constraints on what they're made out of from the size and the observed mass. But for the most of the small asteroids, you can't. The color ends up being a much more sensitive probe of at least the surface materials for the small ones. Yes.
Do we have a decent theory on what's special about that particular distance, that orbit, that it didn't form into some other planet?
As to why it didn't form, it's because it's perturbed by Jupiter. Yeah, so essentially what happens is as Jupiter goes around, it stirs it up. You can kind of think of Jupiter as like as it goes around, because they're not orbiting at the same rate. It's sort of stirring up everything that's going on inside the asteroid belt. And so you can't things can't consolidate enough. As they start drifting together, Jupiter comes through and it's like, nope, pulls it apart. And it also sort of sets the other bound, sets both bounds, because if you go too far out, Jupiter like sucks you in, and either like actually what most likely what happens is you get ejected to the far outer solar system, and that's how we form the Oort cloud. So question back there.
How applicable is this to other bodies? It's like, I don't know, like the moons of Jupiter, like you mentioned, or like other like dwarf planets, like
Okay.
can it tell us anything about that? Or
Yeah, so the people who do this consider anything that isn't a planet, like they've changed the classification a lot. So I say asteroids, but I'm actually including all minor planetary or all small bodies or minor planets, which would include like Ceres and Vesta. One of these plots is actually of Ceres, I think. Where you at? I thought I had a certain plot. Anyway, we do see the minor planets as well. So yeah, we can talk equally about the minor planet surface compositions. Very similar questions there. to the asteroids. We also don't really know what's going on in the regoliths. As to other objects, we don't quite have the sensitivity for most things that aren't asteroids right now. So comets are, as I mentioned, they're a little too faint for us to see. And then there are what we call trans-Neptunian objects, which are small bodies that live at the orbit of Pluto or beyond. And those are just a little bit too far away from us to see right now. However, projection is that the next generation will be good enough to see that. So again, come back in 10 years and maybe I can tell you about TNO properties. But yes, we could answer similar sorts of questions about TNOs if we get the sense.
Is the probability to find asteroids bigger when we get closer to smaller
Radii, like closer to us?
no, I mean, I forgot the word in English or in French. Like the closer they are from Earth, the more probability is big to fall on Earth.
Actually, not necessarily. Whether an asteroid ends up coming to Earth or not is pretty complicated. A lot of the asteroids that are Earth impacting actually come from pretty far out in the solar system because they're more susceptible to be kicked by. They're more susceptible to being kicked into Earth out of their orbit by a gas giant. Orbit, yeah, orbit. So no, actually, it's mostly objects pretty far out that end up on Earth. Not all of them. Certainly, there are asteroid belt objects as well, but a lot of the dinosaur pillars come from pretty far out in the solar system.
How can we determine what asteroids are made of?
Well, that's a very complicated question. The answer is, do I have a good follow of this? How do you actually determine what an asteroid is made out of? So I'm gonna use this plot because it's probably the best way for understanding this. So you can see how certain areas of this asteroid are more red and more blue. This is true of the asteroid in general as well, right? We take color photos of asteroids. Some of them show as more blue, and some of them show as more red. And there are also more complicated things that can go on. So our telescopes see with a lot more wavelengths than we do. So that allows them to see in more detail, sort of what the color of the asteroid is. And that color maps pretty closely onto the material properties, at least to the surface. That we get by just examining things in the lab. Like there's nothing special about the rocks that are in the asteroids are just rocks. And so you can compare that to a lab sample and get an idea of what the asteroid is made of. So in broad strokes, that's how we do it. We look at the color of the asteroid and we compare, or the spectra of the asteroid, and we compare that to other observations.
Do you mean radio spectrum?
No, you can't see the radio spectrum because they don't emit. Because it's reflected, because we look at them in reflected light. It's not actually the emission from the from the asteroid that you see. You just see the spectrum that you sent out at it reflected back at you.
But this is the image of the asteroid with radio waves.
Yeah.
But then how do you see colors?
Oh, sorry. Good question. In the IR, we've got James Webb has like 5 or 6 colors or something like that. WISE had 4 colors. All these IR and optical telescopes have multiple colors that they use.
What is IR?
Infrared. Sorry, I've been bad about that sometimes. Infrared is redder than red. So it's, if you're looking at the spectrum of wavelength, blue is on one side, red is on the other. IR is past red. Yes, in the back.
Rocks on Earth are formed under pressure. So how can asteroids have similar rocks? Because they can't be formed under pressure.
Yeah, that's a good question. I'm actually, so this is going to get to the limits of my knowledge of asteroids. Part of it is that asteroids are highly collisional. So there's a lot of banging together of rocks that goes on, especially in the early solar system. And then the other answer is just that they've had a very long time to compress. The rocks here on Earth are relatively young, and the asteroids are typically of the age of the solar system. So they've had a much longer lifetime. Beyond that, though, I'm not 100% sure. Like I said, I'm a cosmologist coming at this. So yeah, the details of asteroid composition. I don't know. Was there another question over here?
Yeah, I was comparing the moon to an asteroid. What was the difference? I don't know if you're gonna be exact.
Well, I can answer at least a little bit about that. We're almost positive that the moon was formed by a collision of a very large planet with the Earth at some time early in our formation history. And so the moon is composed of almost exactly the same materials as the Earth. That's not true of the asteroids. We know that the asteroids are not representative exactly of the rock that are in the planets. They're representative of the leftover rock. And so that is not exactly the same as the rock that's in the planets. And the ways in which it's not the same are interesting. That tells you about, at some point, essentially, these asteroids stop being able to come into the Earth's orbit and be absorbed by the Earth, which is largely controlled by when the gas giants form and when they move to their present orbits. And so I can't tell you how exactly this works, but the difference in composition between the asteroids and the planets is essentially set by the time that we stopped getting bombarded by asteroids, which is related to the formational time of the gas giants. Yes.
In one of your previous pictures of the cross section
Yeah.
of the asteroid, you see there's like different sections. How solid is the division between each region?
Oh, pretty loose.
It's just
yeah.
very gradual.
Yeah. The regolith is going to be relatively differentiated. So the regolith is subject to a process called very imaginatively called gardening. This is essentially where very, very tiny meteorites, meaning like not even, but like grains of dust, strike the surface of asteroids like very frequently, like all the time. And so that stops that, combined with the very low gravity, stops the regolith from ever really consolidating. So that the regolith is reasonably strictly differentiated because of this process that the interior of the asteroid obviously is not subject to. Further down, though, I think it is generally pretty gradual. Although the asterisk on that is, I believe, and this is absolutely at the limits of my knowledge of asteroids, I believe metallic type asteroids, which I didn't really cover here, tend to have a very metallic core with like dust and dirt on the outside. So there is a transition there. Yeah.
So just below the surface of the asteroid, it's either denser than you expect, colder than you expect, or of a different material than you expect?
Sorry, I should be a little clear about that. Yeah, so the two leading sort of answers are: one, it's a lot colder than we expect. So we have models of heat transfer, yada yada yada, that give us prediction for how cold it should be under the surface. Maybe that those models are wrong, and it's a lot colder than we expect. The other thing that could be going on is essentially that it's actually less dense than we think. Much like I said, it's like semi-transparent, right? And the amount that it's semi-transparent is related to how closely packed this regolith is. Like I said, it's not like dirt, it's very loose. And so a lot of it is empty space, right? And so the density actually, like as you make it more dense, it becomes more opaque, just because there's more stuff there. And so if it's less dense than we expect, then it's going to be more transparent, and that's going to lower the flux that you see, the brightness a little bit. Both of part of the reason why we don't totally understand is that both of those are pretty complicated. It's difficult to predict exactly how it changes as you either make it less dense or make it colder. And so we probably need more data essentially to say that. We need more frequencies of light, really, which is coming online soon. Yes.
When you said that Hubble telescope has 4 colors.
WISE. So WISE, wide field infrared, wide field infrared survey experiment is not the Hubble. It's a different satellite experiment. But it has 4 colors. What I mean by that is that they essentially have they have a camera, and you can imagine you know those like kid lights, those like lights little kids have, where you like put a piece of red thing, like a red plastic in front of the light, and it shines red light, or you put a piece of green light in front of it and it shines green. You can do the same thing with the camera, right? And in fact, if you're into like analog photography, you can get filters that like say reduce the amount of blue light that comes through or something like that. And so you can play with the amount of light that passes through an instrument by putting a filter in front of the instrument. And that's what WISE does. It has 4 different filters that pick out 4 different colors of infrared light. And it puts them in front of its camera, and it takes a picture, and then it switches it for the other one, takes another picture, and then so on through all 4 of the filters. And so it gets 4 images of an object in 4 different colors. So when I say it has 4 colors, that's what I mean.
So will these filters only specific wavelengths from us?
Yeah, that's exactly right.
Why would they do that?
Because they want to understand about the color of the instrument. So there's a trade-off here between total bright sensitivity. So the more light you let through, the more sensitive your instrument is. There's more light. But on the flip side, you can't make comparisons of the brightness of the object at different frequencies if you don't restrict it. Right. So they know that the color of objects like asteroids, but they also study other objects that emit in the infrared. The properties of those objects are often revealed by the color of the object. So they intentionally restrict the wavelengths so that they can get that color information. If you just let all the color through, their detectors are agnostic to the color of light hitting them. So if you just let it all through, you're not going to be able to see any color at all. It'll essentially be a black and white photo of the object, the asteroid of interest. Your camera does the same thing, by the way. It does it in a slightly different way. It has 3 for every pixel. It has 3 detectors that only see 1 wavelength, and then it adds those up. When it shows you the final photo, what it does is add up each of the response of each one of those detectors to a given wavelength, and show it on your screen. But if it didn't do that, it would only be able to see black and white. Essentially black and white.
Is this why the picture, the picture of the dot, and one of the picture is blinking?
Why it's blinking? No, that is not. It's blinking because the distance from us to the object is changing. But this is only one color. This is why this is stuck in black and white, because this is only one color, and so I can't. I mean, I could make it all like different shades of blue, but that would, yeah, that wouldn't. Yeah.
What is the time range of this?
Oh, that's a great question. This is about 3 years. Yeah. So we sped things up a little bit. I figured you guys wouldn't want to sit here with 3 years watching like one frame go by every couple months. Yeah, this is about 3 years of data that it's blinking in and out over. Yes.
I have a question. What is it like working in a field that is totally not what you studied or intended to work in?
It's a lot of like being an undergrad again, a lot of paper reading, a lot of emailing people being like, hey, I have no idea what I'm doing. Would you mind explaining the basics of your field to me? And very slowly. It's a little easier for me because the SPT people did it first. So a lot of the very foundational papers were cited in their papers. So I did a very close read of their paper. That made things a lot easier. And a lot of it's just humbling. Like, it's really pretty humbling to get kicked back to the beginning. Like, yeah, you don't really know anything anymore. But yeah, I think it's good sometimes. You stick in your field too long and like there are accepted wisdoms in your field. You like too long with those accepted wisdoms and you like sort of start accepting them from truth and you get kicked into a new field and you don't have that intuition anymore. And it's sort of good to be put in a position where you can't just be like, yeah, I know the answer. I've been here working in this field for 10 years or whatever. You have to be like, no, I have no idea. Let me go read up about it. So, yeah, it's challenging, but it was a lot of fun.
Just simple question. Was anything learned from the asteroid that fell in Russia a few years ago? Was anything new?
I'm sure I don't know much about that. I'm sorry. No, I'm sure that it does. Every asteroid fall is extremely close. Anything that leaves behind a relic is extremely closely studied, but I actually don't know much about that particular fall.
Currently, are there more asteroids being discovered by robotic telescopes than humans behind telescopes?
Oh yeah, no, there's almost nothing found by manual observation anymore. The way that we look for them now is pretty advanced. You take like images of the sky and then you compute every possible orbit that an asteroid could have, and you go look for asteroids along every possible orbit. And then report back when you find an orbit that looks like it has an asteroid on it. And this is, trillions of orbits. And so, yeah, this isn't really it's something you need computers for. I actually know a fair amount about this because my best friend in grad school did this sort of thing. So he wrote the code that did that.
Some asteroids that we get seen as comets and things like that. I know it's fine after example.
Yeah.
How do we, on that place where you can find the equation of the trajectories?
Yes, you can. You can get the ephemera from JPL, the Jet Propulsion Laboratory. So the keywords that you want are Jet Propulsion Laboratory and ephemera, EPHEMERA, ephemera. Which is a fancy word that essentially means I don't know, sorry if you already know this, but it tells you for other people, it's essentially like a set of numbers that governs the exact orbit of an object. So they have a lookup service. It has a Python interface. If you know Python, it does also have a web interface, which is less convenient, but if you're not coding, you can just go through the web interface. That's how we did all of ours. I spent a lot of time monkeying around in it. So
Thank you very much.
my pleasure. One more question, or do we have time here?
Yeah, like one or two more.
Yeah, we can do it.
What does this stand for?
What stand for? South Pole Telescope. So called because it's at the South Pole.
How about the deep impact thing that just happened? Were you observing that?
Yes, so I know for a fact people are currently working on. So the primary purpose of the deep impact was to study whether we could affect the orbit of an asteroid. However, when the whatever it was, I don't know if you want to call it a lander, that's a bit generous, but whatever it was that slammed into the asteroid, hit the asteroid, obviously it launched a lot of stuff back out into outer space. And they did have an orbiter, I think it's still out there, and the orbiter did observe the impact. And so I know for a fact that there are people who are studying those images because those are really telling about what's going on under the surface of the asteroid, right? You slam something into it, you get a whole bunch of ejecta that's coming off from, presumably pretty deep into the asteroid. I don't know the current status of that. I don't work with those people, and that hasn't been published yet. That's still they're still working on that. But I do know that those results will be available one day. They're working on that right now.
All right, so with
Awesome.
that, yeah, thank you so
My
much.
pleasure.
Let's thank our speaker one more time. I guess the only other thing from me is that this was our last public talk